Okay, so this is the rotational energy topic. There is really not a lot to say here. This is going to go by super quickly. The reason why torque took a long time to talk about was because it was a vector. So there's some interesting sort of conclusions that pop up when you have a vector. But energy is a scalar. So quite simply, there is not a lot to talk about here. And hopefully this topic goes by pretty quickly. So what's different? Previously, when we studied motional energy, it was kinetic energy. And kinetic energy is given by 1/2 mv squared. This is called translational energy, right? It's the energy associated with an object moving forward. However, you can imagine that if you have a bicycle tire, for instance, there is some energy involved getting the tire to rotate. And more specifically, when the tire is touching the ground, not only is the object moving forward, as you can see here by the orange streak, it's moving forward, so it has a little bit of translational energy. The object is also rolling forward. And that's evidenced here by the, oh, you can't see that because I'm drawing in black. And I can't change my color now because OneNote is an amazing program, sarcastically said. Anyway, the object is being rotated as well. So there's a new type of energy. So, but rotation is also present. So therefore, there is a new type of energy. And this energy is called rotational energy. So there's two different types of rotation, as I mentioned. There's translational and pure rotation. So pure rotation occurs, oop, what happened? Pure rotation occurs when the object is simply rotating in free space and not also moving forward. At this type of rotation means that the particle along the bottom is traveling with a tangential speed backwards, but the same tangential speed magnitude-wise as a particle at the top, but obviously in the opposite direction. So you can see here in the diagram, let me erase my markings, you can see here in the diagram that the instantaneous velocity of a particle at the bottom has the same magnitude of vector as an instantaneous tangential velocity at the top, just obviously in opposite directions. However, if you have rolling motion where the object is physically moving forward as well, then the center of axis, or the axis of rotation, the center of mass, COM, center of mass, is actually rolling forward itself. So here, a particle in contact with the ground is traveling backwards at speed v, but the center of mass itself is traveling forwards at speed v. So the net velocity of a particle at the bottom of a wheel touching the ground is actually 0. It's not moving. And you can see that. If you don't believe me, take a bicycle tire, rotate it, and as you're moving the bike along the ground, kneel down and watch the bike tire's particles that are in contact with the ground. You'll see that they're not moving left or right relative to the asphalt. Now, the weird thing is, at the top, the particles at the top are actually moving at twice the velocity that the bike is moving at. And again, this is relative motion, because the velocity at the top relative to the tire is v, but the velocity at the top relative to the ground is going to be the velocity of the top compared to the tire plus the velocity of the tire compared to the ground. So that's going to be v plus v, which equals 2v. Okay, enough of the semantics. Let's just get right to it. We have this pattern where you swap out all of the linear variables with rotational variables. Same pattern now. Kinetic energy is 1/2 mv squared. So the energy associated of a rotating body is 1/2 I omega squared. M goes into I, V goes into omega. Done. If you have a wheel that is rotating forward, that is both translating forward as well as rotating forward, then the sum of the rotational energies represents the total kinetic energy. So this is going to be the rotational energy plus the kinetic energy. And when you add the two of them together, you get the total kinetic energy, the total energy associated with all types of motion of this particle. So here's a very quick example. A uniform ball, and this will be the last example we do, and that'll pretty much be the end of the rotational energy. Everything's the same, conservation of energy is the same, so let's just do this example very quickly, and we can call it a day. A uniform ball of mass m, okay, m equals 6 kilograms, and radius r, okay, rolls smoothly from rest down a ramp at an angle of 30 degrees. The ball the ball descends a vertical height, a delta H of 1.2 meters to reach the bottom of the ramp. What is the speed at the bottom of the ramp? All right, so we start with conservation of energy again. E total equals E total prime. Now, when I write out my conservation of energy equation, I'm going to write out the same one as before, but now we have a new type of energy to include. So I'm going to write Eg plus Ek plus E spring plus E rotational equals Eg prime plus Ek prime plus E spring prime plus E rotational prime plus the work done due to friction. This is the generic, not specific conservation of energy equation. Let's go through and think about what do we have, what do we need, what can we cross out. At the beginning, at the top, is the object rotating? No. At the top, is there a spring? No. At the top, is it moving is it moving linearly forward? No. At the top, is there gravitational potential energy? Yes. Okay. Afterwards, is there gravitational potential energy at the bottom? No. Is it moving forward? Yes. Is it rotating? Yes. Oh, sorry, that's spring. Is it rotating? Yes. Is there a spring at the bottom? No. Is there any work done due to friction? No. So we use our generic conservation of energy equation to set up our starting equation. And we get mg delta h equals 1/2 mv squared plus 1/2 I omega squared. What are we asked for? We are asked for v, speed. Well, we have omega and I to deal with as well. So what I can do is I can convert I and omega in terms of variables from the linear realm using the relationships that we know. So 1/2 mv squared plus 1/2 I omega squared. Well, what's I? Well, I is the moment of inertia of a uniform ball. Let's go back to torque. And let's look up the moment of inertia of a uniform ball. We're almost done, I promise. Here we go. A solid sphere. The moment of inertia is 2/5 mr squared. So let's plug that in. 2 over 5 mr squared, and omega. Note that V equals r omega. That is our relationship between linear motion and rotational motion. So we can use that and plug it in here, and we can get omega is in fact equal to V over r. So this tells me we get mgh equals 1/2 mv squared plus 1/2 times 2/5 m r squared times v squared over r squared. And we can cancel a bunch of things here. So 2 and 2, r squared and r squared. So where does that leave us? 1/2 mv squared plus 1 over 5 m v squared. mgh. The m's can cancel from the looks of things. And we see here that gh is going to equal to 1/2 plus 1/5 v squared. Now 1/2 plus 1/5, 5 is going to be what, 7 over 10. So this is going to be 10 gh over 7 square rooted equals v. So there you go. And if you don't like my messy handwriting, there is the solution there. So you can see kind of how we took one step at a time to swap out the rotational variables in terms of linear variables. Now, what does this mean conceptually? If an object is rotating, part of the energy gets transferred into the rotation and away from the tangential velocity, which means if you have an object that rolls down a hill compared to an object that slides frictionlessly down a hill, the rolling object will end up going slower than the one sliding frictionlessly down the hill, because it has to split some of that gravitational energy into both moving forward as well as rotating. Whereas an object that just slides frictionlessly down a hill, 100% of the gravitational energy can go toward translational motion. So it ends up going faster. Okay, in terms of new knowledge, that is really the only piece of new knowledge there is for rotational energy. The new piece of knowledge being 1/2 I omega squared, and how you just simply add that term into your conservation of energy equation. The rest is pretty simple. I encourage everyone to go back to the textbook and do some textbook problems. This is the last lecture of the week, so you have a good number of days, at least 4 days, for doing torque problems and energy problems, and even going back to do some rotational kinematics problems before Monday's lecture. Okay, guys, this is the end of the lecture. I'm going to stop the recording now, and I'll take some questions.